Welcome back to another episode of Dave Does Math from Home. We are starting a brand new adventure today. This is Chapter 16, and Chapter 16 gets really exciting. We've done vectors, we've done derivatives, we are setting that aside, we're moving on from that. Chapter 16 is where we do integrals. Integrals in multiple dimensions are really interesting. By the time we get to the end of this chapter, we will be doing some really bizarre things with integrals. Things that, if I tried to show you them now, you'd be like, nope, I quit. That's it, I'm done. But don't lose hope. We're going to build up to the really bizarre, weird things using baby steps so that by the time we actually get to the really weird, bizarre things, you'll be like, yeah, that makes sense, I get it. That's the goal. That's what we're going for. To start getting us in the direction of really weird, bizarre things, we're going to talk about integrals, how integrals work, and sort of what they mean. Your standard issue integral, if you're integrating something like this on some bounds, let's remember that this means we have some function between x equals 1 and x equals 4. And we are, if we just do this arithmetic, this calculus, and then there's arithmetic involved, we're getting the exact area underneath this shape on this region of the x-axis between 1 and 4. And we're doing that. The idea of integrals come from Riemann sums, where we split this region into rectangles and use the rectangles to estimate this area. The integral, the exact area, is what happens when you sort of take the limit as the number of rectangles goes to infinity. But the idea of these rectangles is still sort of embedded in the idea of these integrals. This, if you're thinking about rectangles, this is the height of your rectangle. That's your y value. This is the width. When we did Riemann sums, we called this delta x. That was the change in your x values between one rectangle and the next. When you use infinitely many rectangles, the delta x turns into a dx, and that just means a tiny, tiny, tiny little slice of the y-axis, or the x-axis, I mean. So we have this height times width gives us the area of a rectangle. The squirrely looking s means sum, and then this determines your bounds from 1 to 4. And so this idea of summing up rectangles is still very much embedded in the idea of integrals. I know we kind of, that gets backgrounded pretty hard because we're mostly doing these things just thinking about antiderivatives and evaluating the antiderivatives, and we kind of just, we foreground the relationship with derivatives and the fundamental theorem of calculus. But the idea of area and rectangles is still very present. So this is 2 dimensions. When we start doing integrals in 3 dimensions, a lot of these ideas are going to sort of carry over, but they're going to look pretty different. If you have, I am still terrible at drawing things in 3 dimensions, so we'll just say that this is x and this is y, and we're going to have some f of x, y here. So it's going to be some function, some surface wandering around covering this, like some blanket over top of this with various bumps and curves and wiggles and hills and valleys. So we have a surface that exists over top of this plane, or maybe sometimes it exists behind the plane. We'll just say that for now it exists over top of the plane. And the idea of the integral is sort of the same. Here we're looking at everything that's below the line, and that gives us an area. Here we want to be looking at everything that is below the surface, and that's going to give us a volume. So if we're interested to see what's happening in x goes from 1 to 3 and y goes from 2 to 4, this is now the region we're dealing with. Instead of the region we're dealing with being an interval on one axis, the region we're going to deal with is two intervals across two axes. It's going to make an area. And so we're going to see inside this area, or above this area, our function is going to be doing things. We're going to have some surface that's wiggling around up top over this thing. And we want to find the total volume above this area beneath this surface. And that's what integrals can do for us. If your surface is nice and flat, like if your surface is z equals 5, then you just have a flat thing out here. You can sometimes just still use geometry to figure these things out. If your surface is just 5, then you have a rectangular prism, a box. You have a box that is 2 units on this side and 2 units on this side and 5 units tall. So you can just use geometry to find the volume of that. It's 2 times 2 times 5. Pretty straightforward stuff there. Obviously the goal of doing this in Calc 3 is to do it with more complex things where we can't use geometry and we actually do need to use the integral in calculus. So we're going to get right into that. I just wanted to give this this explanation of what we're doing and how it works so that you can connect it to these things. And let's first talk about what the integrals are going to look like. I'm going to say that this volume, to go on 2 different axes to get an area, we need 2 integrals. So we're going to have to integrate twice. As usual, the function goes inside the integral. And because we have 2 integrals, we need 2 d's. When we first started learning integrals in Calc 1, I encouraged you to think about these d's as if the d was sort of an end parentheses towards this symbol. This symbol tells you that you have begun an integral, and this symbol tells you that the integral is finished, and they sort of bracket the thing that you're integrating. And that's, in some sense, that's still true. Like we know now that the d is, sometimes it means the derivative of a thing, if you're doing integration by substitution or implicit differentiation. Sometimes it means like a distance, like this. This is a width. The dx is a width. And sometimes it means the end of an integral. D means many, many things. And they don't always seem consistent, but it is mathematically consistent that it can be all of those things sort of at once. So we can't just have d's here. I have the d's as like little placeholders. We need one of these things to be a dx and one of them to be a dy. And I will tell you that the order does matter. This is not a partial derivative situation where if you want the mixed partial second derivative, it doesn't matter how you get there. When we were doing those mixed partials, you could do derivative with respect to x first and then y, or you could do y first and then x, and it didn't matter, you were going to get the same thing either way. Here, you'll get the same thing either way. So like if you do dx first or dy first, you'll get the same thing. You'll just, depending on which one you choose to put first, that changes how you have to finish doing the problem. So what do I mean by that? Let's just say we want to do dx dy. We could do this the other way. We would get the same answer, but we would change how we approach the problem. So I guess that's what I mean when I say order matters. You won't get the wrong answer if you put it in the wrong order. You just have to do different steps depending on which one you put first. So, if dx is first, that means that dx goes with this one. When you have these double integral situations, or later when you have triple integral situations, you always do the integrals from the inside out, just like parentheses. That's part of why I encourage students to think about this as like it's an in parentheses. So this opens up your integral, this closes it, that is its entire thing. When you're working on this, you can sort of pretend like the outside integral doesn't exist. So this integral with respect to dy, you don't have to worry about that, that's on the outside. First we do the inside. So if this is the x integral, it needs the x bounds. So x here is going from 1 to 3. You don't have to write the x's here. In fact, the book does not. If the book was writing this, it would just put a 1 here and a 3 here. I like to write the x's because it helps me establish that this integral is for this d, and there's no way I can get myself mixed up on that one. That means that the outside integral is dy, and so that's going to go from y equals 4 to y equals 2. Sorry, from 2 to 4. Always start with the lower one and then the upper one. So this is how you get the integral of the total volume of the function f of xy equals 5 over this rectangular region of the xy plane. So let's talk about how you evaluate this. Just like when we were doing partial derivatives, when you evaluate an integral, an integral with multiple different variables, this is the variable that you're integrating with respect to in the first one, and you treat all the other variables as if they were constant. So, in this case, this integral from y equals 2 to y equals 4, and the dy on the back end, that's not going to change. That's the outside integral. I deal with that last. Right now, I'm only concerned with this inside integral. The integral of 5 with respect to x is 5x, and that needs to get evaluated at 1 and 3. So that will give me, let me see if I can squeeze this in over here. That gives me the integral from y equals 2 to y equals 4 of, let's see, 15 minus 5 dy, which is just 10. The integral of 10 with respect to y is 10y. We're evaluating that between 2 and 4. That'll be 40 minus 20, which is 20. So according to this integral, the volume of this box beneath the function f of xy equals 5, from x going 1 to 3 and y going 2 to 4, the volume of this box should be 20, which I think checks out with our geometry because it's 2 times 2 times 5. So yeah, you get 20 either way. But this is how the integral works. You have to set up your dx's and your dy's. If you choose to put these in the other order, that means dy is your inside integral, and you need to put your y bounds here and your x bounds here. So that's what I mean when I say order matters. The order in which you choose to put the dx's and the dy's will determine the order in which you need to put the bounds. And you can switch them if you're feeling very ambitious about it. That's fine. And sort of the same thing happens. You take the integral from the inside, you evaluate that, then you do the outside integral and you evaluate that. Same like normal integrals. I'm going to do a part 2 of this video where I start doing like more interesting integrals so that you can see how I integrate something that's more complex than 5. But this is just to get the idea of it. And before I start that second video, I want to talk a little bit about what these pieces mean, because that's going to become important later when we start changing things. Here we said that x squared was a height and dx is a width, and that gives us rectangles. Here, something sort of similar is happening. I find it best to think of the function as a height and the d's as an area. The function as a height above the xy plane, I think that is pretty intuitive. That hopefully doesn't merit much explanation because the function is a surface above the xy plane, so its value gives a height at any given x or y value. The dx dy being an area is what I mostly want to talk about. Here we said that dx is a tiny, tiny, tiny little infinitesimally small chunk of the x-axis. Just a wee little infinitesimally small. The width is approaching 0 in a limit sense. dy is the same thing. So at any given point in here, you can sort of make a box that has a width of dx and a height of dy. And when you multiply those things together, you have a tiny, tiny little strip one way and a tiny, tiny little strip other way. What you get is a tiny, 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 tiny little box. And when you multiply that area, it's an infinitesimally small area, but that's okay because we're going to add up infinitely many of them to get an actual value like this. When you multiply that infinitesimally small area by the height, that's what's giving you the volume. So tiny little area, length times width times the height gives you a volume. And then these big S scripty S integral things, that means you're just adding up all the volumes. You're infinitely many volumes. So instead of taking the sum of the areas of many rectangles, I think of this as taking the sum of the volumes of many pillars. Like if you imagine, have you ever seen like a whole bunch of pencils of various heights like smashed into like a coffee cup or like a mug or like on someone's desk? And you think about like all those different pencils having different heights and they're all sort of packed in there. That's sort of what's happening here. We're taking a bunch of pillars that all have various heights. Here we go. I got a bunch of markers, so we'll use this. Okay. So we have a bunch of pillars of various heights, and the area of these underneath these pillars is going to be our dx dy. That's a tiny little chunk of area, and they all have heights, which is giving them different volumes. And then when we add up all the volumes, we get the volume of the whole shape. That is the basic idea of a double integral and the basics of how to calculate double integrals. We're about out of time for this video, so expect a part 2 where we'll stop talking about all these ideas and we'll just start doing a bunch of math and going through examples and figuring out how these actually behave when we're working on them. This is how they're set up and what they mean, so hopefully that's clear. If it's not, rewatch this video again because it's going to get worse.